So our goal in lab this week is to make something. We're going to make a coordination compound. And we're also going to identify the structure of that coordination compound using both spectroscopy and computation. So this week, like most weeks, 2 groups will start out in the lab and two groups will start out with the computation, and those assignments will be available on Moodle. It turns out that making a coordination compound really isn't so different from synthesizing anything else like you did in organic. So the first step in synthesizing anything is to mix some stuff up and have it react at some temperature for some period of time. So here, as you read about, you're going to mix molybdenum oxide, sometimes called molybdic acid, with 2,4-pentane dione, sometimes called acetyl-acetone, and you're going to mix that for in the presence of with ammonium hydroxide as a base in water for some period of time. And then, and so as you do that, I want to make sure that you write down the actual amounts of reagent that you weighed out, not just the handout amounts. And at the same time, I don't want you to spend all day at the balance making sure that the actual amounts match the handout amounts. So, get it close, write it down. And then you're going to react it for some period of time. Actually note how long it reacts. Not just I set a timer, note when it starts, and then you can note when it finishes. So once it's reacted for a while and you're pretty sure that it's done, then the next step is the workup. Workup is the part where you separate the product from the reaction mixture. In this case, we're going to make that easy by causing the product to precipitate. So we're going to add some nitric acid, and that will make your product precipitate and you can filter it out. Now, once you have some stuff, then you need to go to characterize it. And so when we're characterizing, there's usually 2 things we're trying to figure out. We want to know the identity, and we want to know the purity. And so, like if we were to publish this in a journal, we would have to establish both of those things. So to establish identity, what do you think we can do? Probably the most common things are spectroscopy. So here we're going to do IR spectroscopy, and we're going to do NMR spectroscopy, just proton. To establish purity, how would you tell whether it was pure? I'm going to leave that one for you to think about. And you can design a very easy experiment for you to do, something you already know how to do, hint, hint, for how you can establish the purity of your compound. Okay, so for working out the identity, we also need to think about how there are 2 possibilities for this compound. The 2 possibilities are the cis isomer and the trans isomer. How are we going to work out which one we actually have? Here's your big hint, only one of them forms. And we're going to use our spectroscopy and symmetry to work out which one we have. And in order to use our spectroscopy, we're going to focus on the MoO modes. So we're going to focus on specifically the MoO stretching modes. So you can use what you know about symmetry and vibrational spectroscopy to calculate the number of MoO stretches. You'll need to find where MoO stretching modes happen in the IR, so how many wave numbers, and you can do that using the literature. And then the last thing you're going to do is you can calculate the stretches and the IR spectrum using WebMO. Now, because these are pretty big molecules, I'm going to give you input files. So on Moodle, you should find a cis version and a trans version. These are the geometries. Your job is then just to calculate the vibrational frequencies. And now these molecules have a lot of atoms. So 3n minus 6 is going to be a lot of vibrational frequencies. And your job is to sift through them and work out which ones are the MoO stretching modes. Because our server is sort of the little engine that could, we're also going to run these calculations at a pretty low level of theory. So while the stretches will be there, the energies at which those stretches occur may be off by about 100 or so wave numbers. So we're going to need to find them. We can use our experimental values as kind of a starting guess, but we'll actually have to look at the frequencies to find them. Okay, so once you've done all that and you've decided which mystery isomer you have, you need to report your results. You have two choices for how to do that. You can either write an article or you can produce a poster. And remember, in the syllabus, which one you choose is going to depend, sort of influence what kind of grade you are going for in the end. Okay, so in either case, you're going to follow the conventions of these modes. So in the case of a paper, that means that your paper is going to have an introduction, experimental, results and discussion, conclusions. If you're having a poster, it might look something like this, where you also have these parts, but they're more graphical. That means you're going to need images. So I want you to make high quality images that you, not just scanned in versions, but I want you to actually make figures, probably using Excel. Or in the case of your NMR spectrum, you don't really have to have a figure for that one at all, but your IR spectrum, you'll want to embed those figures in the document, not just append them to the end. And you will want to use ChemDraw to make any structures that you want to use in order to represent what's going on. I also want you to contextualize your work in the context of the literature. So that means that you're going to need to reference at least 2 reliable journal articles. And when I say reliable, I mean probably things from the American Chemical Society, not just the first thing that comes up on Google. I've Googled this, and the first thing that comes up on Google is a relatively low-quality open access journal. So I think you can do better than that. And so when I say contextualize, I want you to think about why somebody might have done this. So why would somebody be making these molybdenum compounds? What are they used for? Are they pigments? Are they catalysts? Are they biological molecules? And then I want you to write your paper as though synthesizing this complex was part of a research program, your research program. On your paper or your poster, you'll list your name as the first author, but then if you get any help from anybody else, if you get any spectra, or maybe your compound falls on the ground and you borrow some from somebody else, you can cite them as co-authors. So there are more guidelines for what the standards are for your paper or poster available on Moodle. I'm also happy to ask questions about that. The due date is also available on Moodle. And so a last comment is maybe about safety related to these compounds. So when you're synthesizing these things, again, I want you to wear your eye protection and your gloves. There aren't a whole lot of hazards. The main issue here is that we'll be working with a relatively concentrated base solution, that ammonium hydroxide, and a concentrated acid solution, nitric acid. So in both cases, you want to avoid getting those on your skin or splashing them on your face. But otherwise, those are kind of the main hazards here. Remember to put all waste at the end in the Chem 332 waste container, but you can save a sample of your solid compound if you'd like. Do ask me questions when we get in the lab, but remember there won't be any formal pre-lab lecture. So get your questions ready, ask them on Slack, and I'll see you in lab.